me in welcoming our next keynote speaker for the day, Dr. Vipul Arora, Associate Professor, Department of Electrical Engineering, IIT Kanpur. With a background in electrical engineering, his pioneering research focuses on learning based methods for audio processing and computational physics. Dr. Arora's contributions include developing speech recognition systems at Oxford University and advancing audio classification for Amazon's Alexa home security. His expertise in music, speech, and imbalanced data classification underscores his impactful work at the intersection of academia and industry. So, through you, we are ready to take a glimpse into the future and ignite our imaginations. So, please welcome Dr. Vipul Arora with his keynote speech on machine learning and deep learning applications. Over to you, sir.
Okay. So it was very nice talk. The last talk was very interesting, which presented about continual learning and how we can progress towards AGI. In my talk, I'll be complementing that view with human machine learning, that how humans and machines can collaborate together and make very efficient and very effective systems. So Um, so I will, in my talk, the topic is searching big audio data. So let's say we have huge amounts of audio data, and what do we do with it? Now we want to index it, we want to search what is there in the data and mine it, and so many things. So how do we do it? So that's the application, and the technologies which we are using are mostly um, uh, machine learning with human and machine in the collaborative mode. Okay, so what kind of audio data do we have? So we have access to huge amounts of audio data. Like it includes speech, music, different kinds of background sounds like sound effects, etc. And what do we want to do with it? We want to query the data. Do I have a pointer? Where we want to retrieve similar audios. Let's say if I say gunshot, the gunshot audios can come out. Or if I upload some audio and want similar audios from the database. This is the kind of target what we want to build. And that what is the challenge? Okay, so what are the different kinds of search we can do? One is that we can search by audio snippets. It means I can upload some recordings, maybe noisy versions of the recordings, or maybe some snippets here and there from the original audio. For example, television is playing some program. I can use my mobile phone to record a short snippet from there in my mobile phone, and I upload it to the website, and it should retrieve the original audio where it came from. Or I could enter some keywords which are like text words, and I want to retrieve all the relevant audio corresponding to that text. Or I could hum some music. I could make some music on my own, or which will retrieve similar music. So we targeted all these problems. The first problem for that, I will be talking about representation learning for audio search. And then I'll be talking about speech recognition, by which we can create annotation for all the speech, and then we can search it with text keywords. And then I will talk about melody estimation in music, which we can use for querying and retrieving music files. What are the challenges involved? The challenges are we got huge amounts of raw data. There is hardly any label or hardly any annotation associated with that data. So we have to create those annotations on our own. And what do we have? We have a very small team of annotators. So this is the challenge. So I'll start with first the representation learning for audio search. What is the benefit? It does not need annotations. We can work with the raw audio and create some representations which we can use for searching. And we use self-supervised learning methods to get compact representations. Let me introduce you to the problem of audio fingerprinting. So what do we mean by audio representations which can be searched very efficiently? Let's say I have got a huge database of audio files. So, and I have a short query, which is a noisy version or a short snippet from one of these files. So what I can do is, using audio fingerprinting, I will use a machine, which could be a rule-based model or signal processing-based model or a machine learning-based model, which will learn some compact representation of that audio. And it will do it for every audio in the database. And it will also do it for the query which the user gives. This is done beforehand and this is done on the fly. Whenever the query comes, quickly it is encoded into this representation. And then we have a matching algorithm, which should be very efficient because this is like millions of audio files and this is just one small snippet. So very efficient matching algorithm, which can search where is the right match. And it should return that right audio for me. It could be a list of audios, like Google returns a list of relevant documents. So we have two components here. One is this, how do we represent that learning algorithm, how do we learn that encoder, which will create those representations? And the second is the efficient matching algorithms. So let me first discuss a little bit about what is speech. So basically speech is an one-dimensional signal with amplitude, which is varying with time. And how do we analyze it? We take short windows which are overlapping, like the first window, second window, third window. And from every window, we try to compute some features. And we use discrete time Fourier transform to compute these spectra. So in this way, I'm able to represent the time series into kind of series of vectors or a sequence of vectors. There are some existing methods. For example, Shazam is a very popular service available already. People use Shazam to find audio. So this was the original algorithm for Shazam, which was rule-based algorithm. It looked at this DTFT-based representation. It's called the spectrogram, where x-axis is the time and y-axis is the frequency, and you can see how uh, when time is evolving, how the frequency strengths are changing with time. So it used some kind of signal processing or rule-based algorithm to extract um, descriptors or representations. It was all rule-based, based on signal processing methods. Now, what we are trying to propose is, can we learn a representation like this, which is, let's say, xt is my original audio signal, and zt is the sequence of representations. And this zt, this is of dimension m, which is very small as compared to n. And the number of time steps t tilde could be either capital T, same as like let's say my original audio had 10 frames. And from there, I extract 10 vectors, or I can even extract less number of vectors for even further compression. So this is the problem. One method could be I take the audio and I get vector representation. The other method could be I take the audio and I get token representation, which is much more efficient. For example, if I'm speaking something, if you search it directly in the audio, it is much more computationally intensive. But if I use some kind of text representation, the text search is very fast. So can we represent audio with some kind of not man-made linguistic system, but a statistically learned sequence of tokens, the text representation, which is learned by the machine itself from the data. So in the first work, which we did about 2 years ago, so there we learned vector representations. And then we binarized those vectors so that the search is very fast, the matching is very fast. So these representations were learned with something called self-supervised learning. And contrastive learning is a method for self-supervised learning, which means We have just the raw data, raw audio signal, or the raw spectrogram. And from there, we want to learn a machine which can represent it in such a way that even when this spectrogram or this audio has some noise or some time shift, some reverberation, even then it should map to the same representation. So that's the goal of this part, that learn a representation or learn a function f, which can transform my input audio spectrogram to a sequence of vectors, which remain same even when the audio is noisy, reverberating, or has some time shift. That was the goal. And we used contrastive learning with augmentation. Augmentation means we add noise, reverberation, time shift, etc. And contrastive learning is this framework where we take representation from the original audio, let's say xi, and then representation from a distorted version of the same audio, maybe the noisy version of the same audio, which is xi dash. And we want to minimize this distance. And we take xi, the original audio, and xj, some other audio which is not same as this. And we try to maximize this difference. So that's called contrastive learning. And this is a totally unsupervised method of learning. And by using this, we could learn very good representations which were able to beat existing representations. Of course, there are other things like uh, CRNN models, or as you can see here, ResNet models, convolutional models, as well as attention. These things were used as a part of the machine, but the learning was contrastive learning. So the idea of self-supervised learning actually comes from, it started in the natural language processing literature, where we have lots of text, and we can use the text itself to learn good representations. Let's say I have a sentence called, "My name is Vipul Arora," or maybe uh, "I am teaching at IIT Kanpur." This is a sentence given to me. It's a raw sentence. From here, I can construct a task. For example, I can create a blank. Let's say I remove teaching. So I am dash at IIT Kanpur. And teaching is, I remove it and replace it with a blank. And the task is fill in the blank. And by doing this fill in the blank task, the machine learns about the data. That is called self-supervised learning. And I don't need labels for it because I can create tasks on my own just by deleting the words which I already know. And those words serve as the ground truth. So that's the idea of self-supervised learning. And when we used it for this audio representation learning, so we got uh, our top one hit rate, which means the best match is actually the right match. Means our machine returns a list of audio files, and the top file is actually containing my query. So if I measure that top one hit rate, so we can see at 15 dB noise, almost 99% of the times we are able to get the right audio. And whereas with Shazam, the odd F print algorithm which Shazam published in some time ago, there it was 91%. And as you keep increasing the noise, which means the SNR, the signal to noise ratio, goes down, the noise is increasing, the performance degrades, but the performance of our method is not degrading as much as ODF print or Shazam is degrading, because this is a signal processing based method, whereas this is a machine learning and self-supervised learning based method. So the performance is still much better. And similarly, you can see when we add reverberation, again, the 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 performance is much better than Shazam. And if you want to read more about this work, the codes are available on this web page, and a detailed tutorial video is also available on YouTube, which you can go through. So summarizing, so what we have done in this work is we represented every frame of audio with a vector or a binary code. Binary code means 0, 1 vector. And it was very useful for query by example, which means if I have a short snippet from the original audio, I can use it to search that original audio, and when that snippet is noisy. But the question is, can we represent audio with tokens? So we have represented it with vectors or binary vectors, but can we represent it with tokens, which are much more efficient? And also, can humans control what aspects to represent. For example, in self-supervised learning, I don't know what the model is learning, but I only know that, okay, if I have this audio, then it will be matched to the same audio and not to anything else. But for example, I want to now match based on different aspects. I want to match if the linguistic information is same, or I want to match the speaker should be same, or I want to match the acoustic scene should be same. For example, if I'm speaking in a cricket stadium, or I'm speaking in the road where there is a lot of traffic, or I'm speaking in a kitchen, so the acoustic scene should be same, or the emotions should be same. So it could be so many dimensions along which I could say two things are similar. But this previous approach does not give us any handle on that. So how to do that? So we used same idea of self-supervised learning. This is the idea of self-supervised learning applied to audio. It was a work from Google about three years ago, where they worked on where they made a model called wave to vec model, which was able to convert any audio into these representations. So we modified this work to add some more control. So what we did is we took two audio files, let's say X and X dash. So X is, let's say I want to control linguistic information. So when I say, let's say Apple, somebody else says Apple. So this becomes X and X dash now. So I said Apple, somebody else said Apple. So there are times are not synchronized. The content is same, but the speakers are different. The way of speaking is different. The accent is different. So many things are different. So, but how we trained the model is we passed it through some deep model and got some tokenized representations out. And first of all, we tried to add a regularization function, which means if I add some noise, it should map to same tokens. And the second thing we added is a connectionist temporal classification loss, which means uh, if my X gives some sequence of tokens, the X dash gives some other sequence of tokens, then we try to minimize this sequence of token. We try to minimize the distance between these sequence of tokens, the added distance between them. And how we do it is with the help of CTC loss function, which means I try to map this audio to this set of tokens and this audio to the other set of tokens. So this cross mapping helps us to learn very robust representations, which preserve the information which I want to preserve. For example, in this case is linguistic information. If I would have taken this as one speaker, this is another, this as the same speaker but speaking something else, then I could have, when I have ever done this cross mapping, it would have learned speaker specific features, not the linguistic specific features. So that's the advantage of this algorithm, that it gives you more control. Humans can control what the representations actually contain, what semantic information the representations contain, so that we can do the right kind of matching. We have also applied this algorithm for music search, where I may be singing different lyrics, but same melody. So then also they should match to the same representation if I want to do melody-based search. So these were some experiments, and we saw lots of improvement with very small models because we were controlling exactly. So the code repo is available here if anybody's interested. Now, this was all self-supervised learning with little bit of human inputs. Now let's see how humans can even make things much better. So the next application is speech recognition. We have lots of speech audio, and we want to uh, transcribe it into text. So general algorithm is something like this. You have speech and you break it into frames, overlapping frames, then learn the acoustic parameters like the spectrogram, and then pass it through some deep model. It will give you some um, synone probabilities, and you use an HMM to string them together to make first the phonemes and then the words and then the sentences. So that's all is done by, this was the old technology before 2012. And then came, before 2000, maybe 15 something. Then came end-to-end learning, where people said, why to do all these things separately? Why don't we train directly to map the audio to the final sentence? So we are using, so this end-to-end learning is currently the state of the art. And okay, now we have lots of audio. Now somebody may say, why don't you use something like Google or Bhashini, which is already existing in the in the public, why don't you simply use those solutions and apply to your text and get some outputs out of it? So the answer is that these may not work well for the required domain. We want to work on our data, and these models are trained on some other data. And when you transfer these models here, they may not work very well. And we actually tested, and they do not give as good results as we have now. We can use transfer learning. Transfer learning means you train a model on other data sets and then take that model, bring it to your data set, and do some fine tuning on whatever little data you have. That is called transfer learning. Somebody may ask, why don't you use transfer learning? So the answer is it gives one-time output. It's like the machine gives you some output and that's it. So, and in real world, such machines, such models, they have limited accuracy, but we want 100% accuracy, let's say. So how do we achieve that? So can we have 100% accurate machine learning? So mostly the answer is no. But with human and machine collaboration, we can make it happen. So how do we do it? So machines, they give us not only annotations, but also confidence, how much confident the machine is in a particular prediction. That is called confidence calibration. And then the machine improves itself with those human annotations. When machine says, I don't know what is the answer to this, can you correct this for me? Human annotator comes and he or she gives the right answer or the human annotation. And then the machine uses it to improve itself. So this is how human machine collaboration goes. And so we use the word confidence here, confidence calibration. So if we define it mathematically, what do we mean by confidence? So just a very simple illustration. For example, if I have got two classes here, the red class and the blue class, x1, x2 is my feature space or the input, and I want to classify whether it is the red class or the blue class. If I make a neural network, which is like a boundary, maybe a simple linear classifier in this case, which is simple boundary. If I give you now okay, the boundary is x2 minus mx1 minus c, the equation of a line. Now, if I give you a new point and I ask you, is it a rose or a lotus? What will you answer? So most likely you will say it's a red rose. Okay, let's say red point. It's a red star, not a blue dot. And you can tell it very confidently. But what if I move this point very close to the boundary? Now you will say, yeah, looks like it's a red star, but I'm not very confident because it is very close to the boundary. So that is roughly the idea of confidence, how confident we are. And how do we quantify this confidence? We can quantify it by using a sigmoid function, because we know that when the x2 minus mx1 minus c, let's say it's greater than 0 on this side, less than 0 on this side. If it is slightly greater than 0, then confidence is low. But if it is too much greater than 0, which means close to 1, then the confidence is, then the confidence is large. So something like this. So when my h is very large, my sigmoid function is close to 1. When my h is very small, sigmoid is close to 0. And 0 is the boundary. 0 is this boundary. So if it is above 0, my h is above 0, then my sigma is above 0.5. Then depending on how far it is from 0.5, my confidence will be decided. If it is very close to 1, confidence is very good. If it is close to 0.5, confidence is the minimum. So that's what this is the general idea of confidence. Now that sigma h can serve as confidence measure. And in case of multi-class classification, we have a softmax h, which can serve as the confidence. So now mathematically, that was the intuitive understanding. Mathematically, what's the meaning of confidence? So confidence means if my confidence is 50%, it means the probability of my answer being, my y hat is the prediction, being correct, means my prediction and the ground truth, they match. This probability is uh, uh, should be equal to confidence, which means if my confidence is 0.7, then the probability that my answer is correct is also 0.7. So that's mathematically the meaning of confidence. And it's very well, if you want to read more about it, you can go through this reference in ICML to 2017. So on this graph, you can see on x-axis, I have confidence. On y-axis, I have accuracy. If my confidence is 1, my accuracy should be 100% for those points. For those points where my confidence is 0.8, my accuracy should also be close to 0.8. So which means this line is a very important line, that my data, or finally my histogram, should lie on this line. But if it does not lie on this line, this means there's a problem, which means my model is not giving proper confidence output. So these red regions, they show the gap in my confidence model, which means I have a high confidence, but my accuracy is low. I have a confidence of 0.4, but my accuracy is only 0.2, which means I'm overconfident. So generally, models are overconfident. And this was our experiment. We took the softmax score-based confidence, and we saw even when the confidence was 100%, my probability of model being wrong is very large, which means the red ones are the incorrect uh, predictions in ASR, and green ones are the correct predictions. So you can see, even when my confidence is very high, I have large number of mistakes. This is certainly a highly overconfident model, which is giving very high confidence, even when the predictions are wrong. So how do we correct it? So to correct it, we propose something like this. So we have the audio spectrogram as input. We pass it through all that deep network. It gives us some text output. This is an end-to-end learning mechanism. We get the text output. Now, what we do is, in addition to this, we also train another model, which is called world level confidence model, which is a confidence estimation model. It gives us not only the words, also the confidence in every word. And this model, how do we train it? It is trained during the training time itself by using some kind of score. Now, this paper from Cambridge University, it proposed one kind of learning mechanism. They say, just train it as a binary classifier, true or false, which means if my prediction is correct, then the target of this network is correct and it should predict something of that sort. And if the ground truth is wrong, then my confidence model should predict zero confidence. So if we train it like this, then it will learn the confidence values. So this was also a word level confidence prediction model. And but it looked only at the lexical agreement, which means if I said apple and prediction was also apple, then the confidence is high. So, but this model is very poor when the errors are not sparse, which means if the errors are small in number, model works very well. But when the errors are too many, then this kind of training does not give good results. For example, this example, you can see that this is a real example from our data. This was a pre-trained model, pre-trained on some other data set and then applied to our model. And you can see that here, even the small amount of mistakes are also able to distort the word completely. And our targets are so bad. And when we train our confidence model with this kind of target, then the performance is very bad. So what we did is we proposed a new kind of confidence score, which looks at not only the lexical agreement, but also temporal agreement. So the details are there in this paper. But what was the outcome? This was the outcome, that when this confidence is high, there is a high chance that my output is correct. When the confidence is low, there is a high chance that my output is incorrect. So, and when you look at this confidence versus accuracy plot, it is very close to this line, the 45 degrees line here. We tested with Hindi and we saw the improvements. The word error rates went down, and compared to other state-of-the-art models, the word error rate was very small, character error rate was very small. We tested on Tamil with this kind of mechanism. The improvement in accuracy was so much by this active learning. We used Kannada, and so we have this whole setup is available in a software which is available online, mvag.com, and it uses this confidence measures. Like you can see that it don't not only gives you the text prediction, but also the confidence that this word looks like an incorrect word, and you can correct it manually here in the right here. And finally, I will tell something how we use human machine collaboration for melody estimation. So what is melody? So I'm singing ha ha ha. So is my audio shared? Share computer sound. Can you hear my computer voice?
No, Professor Vipul, your computer's audio is not there.
Mhm. Okay, maybe I'll just skip this part. So if I sing something, so you can see the pitch is low, pitch is gradually high, sa re ga, pitch is very high. This blue line is called the melody, roughly. And this is a software which extracts the melody. It does very good job. But as soon as you move to some music where you have lots of background sounds and it's very complicated melody patterns, then the software does very bad. So now you want reliable 100% accurate pitch estimations and you don't have it. How do you do it? You use human machine collaboration. So what we have done here is the same thing. You have the classifier or the melody estimator, and then you have confidence model, which will estimate the confidence. And we develop a framework called active meta learning, which it generates melody estimation plus the confidence value. It recommends the low confidence regions for manual correction, and then when the manually it is corrected, means some human user corrects them manually and gives it back to it. It uses an adaptation system called meta learning based adaptation model to train the model on those new annotations and then give better output for the entire audio. So that's something. I'll skip this part. This is a mathematical meta learning framework. And these are the results. So you can see here, this green curve is this model, the meta learning based adaptation model. And this is manual annotation. So if I start with, let's say, Prat or Melodia, these popular tools, I start with them and then I do manual annotation. It takes, after 10 minutes, I reach this much accuracy. But if I use this kind of annotation tool where you have adaptive meta learning based active learning, there very quickly you can rise up to very close to 100% accuracy, and with very little effort you can go very close to 100%. So that's the advantage. So this tool is also available online. Means we have submitted a paper. It's still under review. So once the paper is accepted, we will make this tool also public. There's a YouTube video which is a tutorial which we gave last year on meta learning. Yeah, thank you very much. So this is our team who did this work, and we were sponsored by some of these agencies. Thank you.
Thank you, Professor Vipul. A great session about this audio and contrastive learning. So I had one doubt in my mind that you anyways clarified during your session itself, that it all depends upon the environment in which the audio has been presented, whether it's in a closed room, whether it's in an outside area. But if we have to consider some emotions, I mean, one sentence, if I see, wow, uh, what a beautiful day. And if I say, wow, what a beautiful day, I mean, there is a difference. There may be a difference in an exclamation mark or a punctuation mark or anything. So, how that is considered, I mean, how we can get accuracy while converting from, audio to text in that case, considering the sentiments, considering the tone, considering, the way the person speaks.
Yeah, good question. So, sentiment analysis and uh, emotion recognition, it's a very vast area of research, and people are working in those areas where they try to map the the audio not only to text but also to the emotions associated with it. And generally, it is very difficult to even annotate those emotions. Even the annotation is so difficult, and you will see there's a lot of disagreement even amongst annotators when they make this. So there are very some robust methods which have been developed at least to annotate the data properly. And once we have the annotations, then of course we can use all these things like either supervised learning or even human machine collaborative learning to further make the machines better.
Right. Thank
Thank
you,
you.
Professor Vipul. Thanks for your time. It was really a great, interesting session. And MWork AI is definitely a beautiful, amazing, work that has been done. So sometime back, I tried looking out for it and working on it. But soon we'll connect, on this part, and hope to have a great association with you and a lot of learning from you further in this area. So
I'm
thank
sure
you
I
very
will
much
learn
for
more.
your time.
Thank you. I'm sure I will learn so much from you as well. Thank you so much.
Thank you, sir.